Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight, it is my pleasure to welcome Darren Croft, professor in the Department of Anatomy at Case Western Reserve University in Cleveland and a research associate at the American Museum of Natural History, the Carnegie Museum of Natural History, the Cleveland Museum of Natural History, and the Field Museum. As a researcher and educator, he mainly divides his time between teaching anatomy to medical and graduate students and studying the anatomy and biology of extinct mammals. Tonight, he will be telling us about climate change, past, present, and future. Please join me in welcoming Dr. Darren Croft.
Thank you very much. It's a real pleasure to be back in front of this group. It's been a little while since I've done this. Last time I think I was talking about mammals, but now for something not entirely completely different. I think hopefully by the end you'll be convinced that I do know a little bit about what I'm talking about when it comes to climate change. But for those of you who haven't heard me give a talk before, I do want to give a little bit of an introduction of who I am and what I do. This is what makes me happy. This is me doing field work, finding fossils. I'm interested in things that have been dead for millions of years, mostly mammals, and mostly in South America. That's what you're looking at there on the right is a small mammal jaw. And this is the basis of my field, which is really fundamentally paleontology. Going out to the field, finding fossils, this is field work. But that's really where the work starts. From there, I do a lot of analyses that try to figure out how species are related to one another, identifying new species, comparing them to the ones that have been there before, and this is known as systematics. Systematics builds on the fossils that we find through field work. But what really got me interested in paleontology isn't so much naming species, figuring out evolutionary relationships, but rather fleshing out bones and asking questions like, what did this animal look like when it was alive? What did it eat? How did it live? How did it move? And this is the realm of paleobiology, really taking bones and bringing them to life. And there are all sorts of different analyses that you could do for that. But when you've done the field work and you've done the systematics and you've done a lot of paleontology, then you can integrate it with data about the climate and really start to answer the big questions about why did ecosystems evolve in a certain way, or how did habitats change in one particular place over millions of years? What did the rise of the Andes do to circulation patterns throughout the world? And this is the realm of macroecology. And because of that, I'm just as interested in ancient environments as I am in the animals that lived in them. And my ideal scenario is to be able to flesh out pictures like this for a variety of time slices throughout the past 65 million years in South America. I've got a lot of work to be able to do that, but this I think is a pretty good estimation of what we think Patagonia looked like 35 million years ago. To be able to paint a picture like this, we need lots of information from the fossils as well as the soils and other types of data in which they're found. And this is a relatively open habitat, we think, probably a relatively moderate temperature and precipitation. And this is maybe what you see if you were to go back there in a time machine. But you might be just as likely to see something like this, a torrential downpour that floods the river and maybe inters a bunch of bones that we can later find as fossils. And this really, I think, highlights the difference between two key terms that I want you to walk out of here knowing the difference between. And that's climate versus weather. And climate is what you expect. When we go down to Chile to look for fossils, this is what we expect. It's a Mediterranean climate. It's hot and dry in the summer. That's why we go there in the summer. It's a wonderful place to work. Weather is what we get. It doesn't always match up. And there's a lot of variation. And there's a big difference between the two. The challenge for appreciating climate and climate change is that we don't really deal in climate. We deal in weather. Do we need a coat when we go outside? What's it going to do tomorrow? We don't think about, oh, how is the average temperature of this year compared to last year? Hopefully by the end of this, I'll give you a little bit better appreciation for that. The question then is, what is climate? Climate is average weather over many years, many, many years. And we can study it at various scales. And we'll talk a little bit about the scales that we can study it at. And one of the key characteristics of climate that we can measure is temperature. Therefore, lots of the graphs that I'm going to be showing today deal with temperature. We can also measure precipitation. That can be a little bit more of a challenge, and a lot of other things are more challenging. So a lot of times when we talk about with climate, we start with temperature. One time scale that we could look at would be historical, hundreds of years. More than one person's lifetime, but just a few people's lifetime. And this is a graph of average temperature over the past 1,000 years or so on the historical time scale. And you can see that there are some ups and downs. There was a little ice age that took place 1600 to 1700 AD where it was relatively cold, and then a medieval warm period earlier than that where it was relatively warm, a degree higher, not even. But when we back out a little bit and compare this to the millennial time scale, which is thousands of years, we really appreciate that what looked like big variations were really relatively small. This green box is the exact same box that we were looking at in the other graph on a different scale. There's our medieval warm period and the little ice age. There's a Holocene maximum that took place 6,000, 5,000 years ago that was warmer, and a Younger Dryas, which was a much colder interval. And we'll talk about this a little bit more later on. This shows the average temperature over the past 18,000 years, back when we had glaciers. We can zoom back even further. This is on the orbital time scale, where we're looking at hundreds of thousands of years. And again, that blue box represents what you just saw in the previous graph. And all those ups and downs have really almost disappeared in a whole series of cyclical ups and downs. This goes back to 1,000 years, so 1,000,000 years are represented right here on this graph. And this is what I usually deal with. That little pink box is what I just showed you, 1,000,000 years. 1,000,000 years, that's not that much for me. I deal in 5 million, 10 million, 20 million years. This is the past 65 million years, basically from when the dinosaurs went extinct to where we are today. And again, all those ups and downs that you just saw, you can't even appreciate on this graph when you put it in the context of the past 65 million years. Therefore, when we talk about climate, we have to keep in mind this idea of scale. And big changes on 100 years may not be big, or they may be very big compared to what we see in the historical record and the geological record over thousands or even millions of years ago. And we'll talk about this graph in a little bit more detail later on too. What I think would be more useful to talk about now is really how do we make these graphs? How is it that we measure climate? And these are a variety of different ways that we can use to measure climate, going from the shortest time scale at the top down to the longest time scale at the bottom. In terms of year to next, all you need is a thermometer, right? Some sort of instrument, and you can pay attention to that. We can use historical records. But if we want to go back further, thousands of years, we need to look at things like ice cores and lake sediments. Sometimes you can use tree rings, but we're really pushing the edge on those. In millions of years, what I deal with, we're mostly looking at ocean sediments and continental coastal sediments. And if you want to go back to 1 billion years, there aren't many places where you can really do that. A few continental areas, but that's about it. We're going to focus then on those big ones in the middle where we're looking at thousands to millions of years. And I do want to point out these are all proxies, right? The only way we can measure temperature directly is with a thermometer. However, we can use relationships, chemical relationships, biological relationships as a proxy, as a way to get at temperature in the past, even though we can't send a thermometer back in a time machine. And all of these are different sorts of proxies. Ice cores are pretty cool. These are pictures of taking an ice core. You can drill down into the ice, and it is a record of past climate. Mostly this is done in Antarctica and in Greenland, where we have thick layers of ice that have been around for thousands and millions of years. Up to 2.7 million years. This is hot off the press. This is how far back the latest ice core has gone. And it's not a complete one. It's one that went over the edge and bent. But we have samples that go back of ice 2.7 million years old, which is incredible. And we can look at the isotopes in there. The other neat thing we can do with ice is we can look at air that is 2.7 million years old. This is not a proxy for air. This is air that was trapped in the ice when it formed. And all those little bubbles that you see there are paleo air, which is really neat. If you want to know what carbon dioxide was like 1 million years ago, you get million-year-old ice. Of course, it's not easy to do. Ocean sediments are a really great record because there's a constant rain of sediment that creates an almost continuous fossil record. And you can do similar sorts of coring on the bottom of the ocean, but it goes back 2 orders of magnitude, 170 million years. And 1 centimeter of sediment is equivalent to 1,000 years in these deep ocean samples. They're not only thick, they're relatively detailed. And what we study aren't really the sediments themselves, but rather these tiny shells of things called foraminifera, which are little single-celled organisms that secrete, I think it's fair to say, beautiful shells that you can analyze. And these shells are made from chemical reactions with the water. And the shell preserves a record of water chemistry because it has to rely on that water to be created. And mostly what we look at are oxygen isotope ratios. Just a little bit of chemistry. I'm not a chemist, so we're not going to get too far deep into this. But there are two isotopes of oxygen. These are stable isotopes. Regular oxygen has 8 protons and 8 neutrons. That's what makes it oxygen. But there is a heavy oxygen, 18, that has 2 extra neutrons to it. And that's much rarer in seawater. And there's an interesting relationship that when glaciers form, when ice form, it preferentially takes up the light isotope, which means by looking at the ratio of the light to heavy isotope, you can get some idea of past temperatures. And this is a little cartoon that I hope makes it a little bit clearer. There, those little things that look like Mickey Mouse, those are really water molecules. That's an oxygen and 2 hydrogens. The blue are the light, and the red are the heavy. And this is normal oceans like we have today in an interglacial period. When we get big glaciers forming on places like Antarctica, they preferentially take up the light, which is the blue, which leaves those red, which then form a somewhat greater proportion of the total oxygen isotopes that are in the water. And we can look at these changes over millions of years to get a very good sense of how temperature changes. And that's how we make those graphs that are 65 million years long. Lake sediments are very useful. We don't usually look, well, we can look at isotopes, but one of the neat things you can do with lake sediments is we can look at pollen. Pollen can be identified very specifically to the plants that it comes from, and since those have specific growing characteristics or conditions in which they thrive, we can use that to reconstruct past temperature and humidity precipitation. For me, one of the questions I like to ask is, how do mammals respond to climate change? There are a few different things they could do. One is they can relocate. This is a picture showing different caves in the eastern half of the US, and these caves gradually accumulate bones, and we can look and see how mammals change through time. And if we're looking in what I call shallow time, thousands of years, going older like this, we see some changes in the mammals. The green ones are ones that are found in that area today, whereas the other colors represent animals that live to the north, to the south, or to the east. And we can see that as we go back further in time, we see other colors, which just shows that these mammals are shifting their ranges as the climate changes. Mammals can also adapt. Body size is a very common way that mammals adapt, and various studies have shown that coyotes change their body size with changing climate, although it probably turns out that other factors were involved too, but this is a common response in many mammals. And then, of course, unfortunately, extinction is another option. And this is a glyptodont, one of my favorite animals. This didn't go extinct due to climate change, but it represents that, unfortunately, this is one way that animals can respond or not respond. An important point is how a mammal responds depends in part on the time scale that we're looking at. If we're looking at a historical time scale, what we typically see is small genetic changes. This is Old Faithful because Yellowstone has a variety of sites where you can look at historical records to see how mammals changed. And there have been studies that looked at pocket gophers and meadow voles over thousands of years, see how they responded to medieval warming, and they found that really what you see are just small genetic changes, nothing very big. When we go back in time to an orbital time scale, thousands of years, usually we see small morphological changes. Similarly, we'll see body size changes like I talked about with the coyote. Noticeable changes, but not speciation. It's only on the tectonic time scale, when we look at millions of years, where we see new species forming. This is a mountain beaver. It actually doesn't live in the mountains, and it's not a beaver. It's not a very well-named mammal. But it's a cool mammal nonetheless, a member of its own family. It lives out in the Northwest in Oregon. And it has even more interesting relatives, these horned animals called mylagolids, horned rodents. You can see a fossil of one, by the way, in the fossil hall here. And we're looking at the past 30 years, and what's highlighted here is that we see lots of species that formed right about when we get a warming 15 to 17 million years ago. But this is the scale that mammals need to be able to speciate and react to climate change. With that, I'd be happy to take any questions that you might have, and we could talk a little bit more about horned rodents, about climate proxies, and of course I'll provide more information in the next 2 sections that'll elaborate on some of these too, but I'd be happy to take any questions that you might have.
Could you explain that graph,
Yes.
it doesn't make sense to me. Thank you.
Yeah, it's a very good question. I got to say, these are graphs that I look at all the time, so I don't even think about them. This is a diagram of evolutionary relationships among these different animals. And all those little names you don't need to worry about. Those are different species within this group. And those lines connect up different species and show how they're related to one another. There are thin lines on that graph, and there are thick lines. The thick lines represent the fossil record, where we've actually found them in time. And I should orient. Old is to the bottom, recent is to the top, just like we find in the paleontological record. So virtually every graph I show will have old at the bottom, new at the top. So as we go through time, we start off with just a very few species. And as you'll see, when we get up to that orange box, all of a sudden we have lots of different lines, both from the fossil record, which are those thick lines, and then the thin lines are species that we have inferred existed based on evolutionary relationships, but for which we don't have a fossil record. They're called ghost lineages, and we do that a lot. This is a way to fill in what's otherwise a pretty patchy fossil record. And if you look at the number of lines, and I don't even know if we were to count how many lines there, you'll see that there are more lines in that interval than anywhere else on that graph. And then they end, which suggests we had a proliferation of species during that period of time. They did pretty well. And then many lineages went extinct thereafter. There are a few that went on, and then finally the last one, if you look at the highest line, it's about 5 million years. That's when the family finally went extinct. But this is essentially a fancy family tree, and we call it a phylogeny, which is just a picture of evolutionary relationships. Thank you for keeping me honest on explaining my graphs.
In the ice cores, you look at the air. Are you looking at the carbon in the air?
That is one sort of analysis that can be done. Yep. You can look at any compounds in the air. Carbon dioxide, that we'll talk about more, is the principal thing that will be analyzed if we want to see how carbon dioxide changes. But you could look at oxygen levels. You could look at helium levels if you really wanted to. That's one thing that we do. And then in the ice itself, we can look at those oxygen isotopes that are part of water molecules. Because, of course, ice is just frozen water, and we can do a similar sort of analysis like we do for those little foraminifera, which means you can look at both the gas and the ice itself.
I believe they just found a remnant of a fossil that's 2 billion years old. So this has been going on, for, at least with life forms for 2 billion. What I heard was that there's like 6 periods or so of extinction during that time. And that extinction is natural for 99.9%. So should we not worry about extinction is, I guess, my question. And why did it happen 6 times over the normal live, living things from prokaryotes on?
There's a lot of question there. The short answer is extinction is part of life, just like death is part of life. It is perfectly natural. But we have 2 types of extinction. It's not all equal. We have what's known as background extinction, which is the normal ebb and flow of species. And a mammal species typically exists 1 million years or 2. If we look back through the fossil record, that's the average lifespan of a species. But then you have mass extinctions, where the rates of extinction in terms of the proportion of species are much higher than the background. And those are the 6 events that you're talking about. There are 5 big ones that occur when we've got multicellular life, and I think there's one that's earlier on. And for the different extinctions, there's a ton of debate about what causes them. And they all probably have different causes. Most of them are probably a confluence of different factors that then combine to result in a mass extinction. And that's one challenge with assessing the extinctions that are going on now, is with just a small point in time, relatively speaking, how much higher than the background rate are we in what we're calling now the present 6th extinction, which I think would be the 7th if we had one much, much earlier. And all indications say that the rate is much, much higher than we see in background, and that it's typical of a mass extinction.
Thank you for joining us. You've been watching Dr. Darren Croft discussing how we know that the Earth's climate has changed over the course of geological time. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Croft will discuss how and why the Earth's climate has changed in the recent past. the last million years. Now, back to the talk.
The recent past, quote unquote. Keeping in mind, recent for me, 10,000 years. Very recent. This is a different version of the same graph that I showed before, which shows average temperature throughout the world for the past 65 million years. And we're going to walk through it a little bit more. Time, of course, is on the bottom, and then temperature is on the y-axis there with warmer temperatures towards the top. And we can basically divide this into two sections. The first 25 million years or so is a greenhouse world. And since then, since about 33 million years ago, 34, we call it an icehouse world. That greenhouse world, you'll see, is characterized by relatively high temperatures, whereas the icehouse world is relatively cold. And when I say relatively, we're talking within the last 65 million years. This is where we are today. Pretty cold in the whole scheme of things, at least, again, relative to the Cenozoic, which is what we're looking at right here. And that's just to give you a little bit of context of where we are overall. I do want to point out this bar, which is interesting. That represents the Antarctic ice sheet when we get glaciers on Antarctica. And you'll notice that it just begins right there at the greenhouse-icehouse transition. And this probably isn't a coincidence. The initiation of glaciation on Antarctica is due to what we call tectonic changes. Changes in the position of the continents that changed global circulation patterns. And what happened is Antarctica became isolated at that point. We start to get this circumpolar, circumantarctic current that isolates Antarctica, and that's when glaciers started. But that changed climate from then on out, and ever since then we've been in an icehouse world. So if you wonder how does this transition occur, how do these major transition occurs, it's with big changes in the continents, which of course only happen over very, very long time scales. Now we're zooming back in. We're going in reverse. This is the last million years. And if you look at this graph, hopefully the one thing that you take away immediately is that you've got a lot of oscillations. And you might be asking, what is it that causes these oscillations? This is a pretty regular, I think you'd agree, up and down. I mean, there's some variation in there, but it's pretty predictable up and down. There are two main things that we think cause these oscillations. One is changes in solar radiation, which is known as insolation. And these are related to what's known as Milankovitch cycles. And Milankovitch cycles describe changes in the orbit of the Earth around the sun, because of course the sun provides virtually all of the energy for our Earth. One of these is eccentricity, which has a periodicity of about 100,000 years. And this is the change in the shape of the orbit, whether it becomes more or less elliptical. We can change the tilt of Earth's axis. Right now it's about 23.5 degrees, but it can vary from 21.5 to 24.5 degrees. And then there's this thing called precession, which for me was always the most difficult to figure out, but it's basically where the Earth's axis points. And right now it points towards Polaris, the North Star. But it hasn't always been the case, and it won't be the case in the future. That can also change. And these three work together to vary the amount of the sun's energy that hits the Earth in different places. And because the continents and the oceans are distributed differently throughout the Earth, that will have different effects. But this, since these are all periodic cycles, contribute to this cyclicity. Atmospheric carbon dioxide is the other big thing. This is actually two graphs. One of those graphs is carbon dioxide, and the other is temperature. And that's why they're labeled on both y-axes. And it doesn't really matter which is which. I think you'd agree, you can't get a heck of a lot more tight correlation than between these two, but these are independently measured things. And we think there's a feedback going on here where temperature affects carbon dioxide affects temperature, and that's something else that we'll talk about a little bit more. But this has a huge effect on the cyclicity of temperatures. A neat example of this, of how carbon, specifically carbon dioxide, can affect global temperatures is the Paleocene-Eocene thermal maximum. And this is a sudden spike in global temperatures and carbon. It actually was recognized by what they call a carbon isotope excursion, a change in the ratio of carbon isotopes that occurred about 56 million years ago at the transition between these two epochs. Here's that same graph that I've showed a few times, and just to point out, that's where the PETM is. And if you look closely, hopefully you can see that blue line really spikes up and then goes back down. This is a geologically instantaneous event. We're talking a couple 100,000 years, which in terms of 65 million is not very much. What caused it? For a long time, we thought, well, we knew it was some sort of big release of gas. We thought it might have been methane released from the bottom of the ocean. But it's very controversial. It's discussed. There's an article that came out just a few months ago in Nature that suggested a very large release of mostly volcanic carbon during the Paleocene-Eocene thermal maximum is what caused this. A big volcanic eruption adds gas to the atmosphere. This causes a spike in temperature. It eventually recuperates, goes back to normal, but it takes a while. Not very long in terms of geological time, but pretty darn long in terms of our lifespan. And of course, the reason CO2 can affect temperature has to do with the greenhouse effect. The greenhouse effect is where certain gases, particularly CO2, trap some of the reflected radiation from the sun and reflect it back down to the Earth's surface. Greenhouse gases are not bad in and of themselves. Without greenhouse gases, we would be a very, very cold place. I think it's minus 18 Celsius or something like that. Very, very cold. But you don't want too many, because then you end up like Venus, which is also not a very hospitable place to be. We want this sweet middle ground, which we seem to have for a number of million of years, mostly thanks to the levels of carbon dioxide that we currently have, or had until a few decades ago. The climate oscillations then that we see are caused by these two factors, sun, insolation, and carbon dioxide, that work together, and what they create are what we call glacial cycles, related to glaciers. And those are the big spikes that you see there in the middle. Therefore, when we talk about relatively recent climate, we mostly talk about glacial and interglacial periods. This is where we are right now, or we were a few years ago. We are in an interglacial period. Relatively small amounts of ice. Here we're looking at the Earth essentially from the North Pole. And there's some ice there, but it's not a lot, particularly when we compare it to a glacial interval. If we go back 25,000 years to the last glacial maximum, this is where ice extended. Ice got all the way down into Wisconsin, into northern Ohio. This had huge effects, and this is typical of a glacial interval. But it's not just about ice. There are a variety of other changes that take place between glacial and interglacial cycles. One is sea level change. And for example, this is the coastline of Florida, indicated by that green arrow, and you can see that, hopefully you recognize that brown line. Particularly, I imagine some of you maybe in February might be heading down to this neck of the woods. Nice place to be in Ohio winters. Well, if you were to go there about 20,000 years ago, you'd have many more places to vacation. This is where the coastline was. And that's because glaciers are made of ice, and ice needs water. Where does it get the water? It sucks it up from the ocean. Therefore, glacial interglacial cycles are not just changes in temperature. We see huge changes in sea level, particularly along the low coasts. Conversely, if you go back 125,000 years to the maximum extent of the last interglacial, Florida's a heck of a lot smaller, just that area in orange. And this is something that could happen if lots of the glaciers melt. And this is a major concern, rising sea levels. The other difference we see between glacial and interglacial intervals is changes in vegetation. And there's a lot of information in this map. What I'm going to call your attention to simply is this spot right here. That's us, that's Ohio. And if you look at the key, it says taiga. Taiga is essentially boreal forest. Lots of conifers. If you go out to Colorado, go up into the mountains, that's what it looks like. This is what Ohio looked like during the glacial interval if you were just south of the ice sheet. And glacial intervals compact all the different vegetational zones into a smaller area. Here then are these glacial interglacial transitions, and what I'd like to call your attention to is the shape. Those stars represent the bottoms. That's the coldest period before it starts to warm back up again. And what you'll notice is it's kind of a jagged downhill slope, but then it's a very steep uphill warming. Therefore, getting cold and getting warm are not symmetrical. And what we see is that the rapid warming that follows a glacial period takes place over about 10,000 years, which is much quicker than the cool down that resulted in the formation of the glaciers in the first place. Why do they warm so quickly? It has to do with feedback loops. And I'm not going to, I thought about doing a feedback loop. I'm going to spare you that. I think you all know what a feedback loop is like. But there are a couple different feedback loops that we think operate to create quick warming. One is what's known as the ice albedo effect. This has to do with the fact that snow and ice reflects much of the energy of the sun, 80 to 90%, depending on where you look. And you can appreciate this when you go out on a bright sunny day and there's snow on the ground. You can barely see. You really need those thick sunglasses, and that's because a lot of the energy is being reflected back up. Conversely, water and soil absorb 70 to 80% of the heat. Very different amounts of heat then are being transmitted down. The reason that this is a feedback loop, you can imagine, is that if you start to get a little bit of melting and you expose the ground, that gets much, much warmer than the surrounding snow, which then increases the temperature, increases the melting, and it's like a snowball going downhill. This is, I think, a good photo for illustrating that. This is from some of my field work in the Andes Mountains of Chile. And we'll go there where snow is up in the mountains year-round, and you'll see what looks like a little meteorite there in the front. It looks like a meteor fell down in the middle of the snow. That's not what this is. This is just a rock that probably fell down from a higher slope. Here, if we zoom in, you can see, but it's in this crater because that little piece of stone sucks up so much radiation that it's like a little oven that then melts this entire crater next to it. This is a great example of the ice albedo effect. Another way to look at it, you can imagine that if you have a glacier, you get a little bit of exposed ocean. That ocean is going to suck up more of the heat, and as you go through time, pretty soon the amount of exposed ocean is going to increase, and you rapidly melt that ice, resulting in calving of big areas of glaciers. The other feedback loop that we get has to do with carbon dioxide, and this is mostly a chemical attribute. Basically, warming oceans release stored CO2. And this is a graph of CO2, carbon dioxide, there on the left, with higher amounts towards the top of the graph. And there's temperature, with warmer going towards the right. And if you trace this line, as we get warmer, the amount of CO2 that can be stored by the oceans goes down. Therefore, you warm the ocean, it releases CO2, and we know what CO2 does. It acts as a greenhouse gas. This is lots of equations that we're not going to go over. But the point of it is the ocean is a big store for CO2, and this drives that equation in the direction of the arrow, with CO2 going from the ocean into the atmosphere. And as I said earlier, CO2 is a major greenhouse gas. Therefore, you increase greenhouse gas, that makes for a warmer climate. Warmer climate does what? It warms the ocean. And therefore, you get another positive feedback loop. And we think that these two operating together cause the rapid warming. Now, it's not always 100% of the time that we get a really rapid warming. There's this thing called the Younger Dryas that we can talk about. And it's interesting. It's an abrupt cooling event that took place 14,500 years ago. This is after the maximum of the glaciers. We were warming up, and then all of a sudden we had a dip in temperatures. And that's what we're looking at in the graph there. That blue shows a dip. The reason it's called the Younger Dryas is that it took place during this post-glacial warming, and it's named for this flower. This is an alpine flower. You could find fossils of it in Britain when there were glaciers there. It started to go away as the climate warmed, and then boom, it came back, which indicates this warming. That's why it's called the Younger Dryas. It was then followed by very abrupt warming. So even though we had this dip down, then we had really dramatic warming. I would say dramatic, 10 degrees Celsius in 10 years on Iceland. Fantastic to think about. I mean, not necessarily in a good way, but incredible to think about warming taking place that quickly. Why did this happen? Well, it's complicated. But it seems to be related to glacial meltwaters that dumped into the North Atlantic rather than the Mississippi. And I will spare you the details. But what I put this graphic up there to illustrate is that the oceans do a lot of mixing, and much of the heat of the Earth deal with waters of the ocean. And there are circulations not only on the top, but also in the bottom that are related to both temperature and salinity. And this is known as thermohaline circulation. And if you dump a bunch of fresh water in at a certain point, like we think happened here, it messes up that thermohaline circulation, and that can have huge downstream effects. And that's what we think happened with the Younger Dryas. All this fresh water went in, and even though the system was warming, boom, it messed things up, and it forced global climates cold again. But we were eventually able to recover, thanks to the mechanisms that we naturally have. So in summary, for recent climate, Climate change has occurred frequently and regularly. That's the graph that we showed before. This regularity seems to be based on finely tuned feedback cycles, particularly with the sun and with carbon dioxide. And small changes in the carbon cycling and ocean circulation can result in abrupt changes in climate. If you have enough time, the system can go back to equilibrium, but it really depends on having enough time. And speaking of time, we have time now for questions.
So we hear that the carbon dioxide is being absorbed in the oceans right now dramatically. I'm sure you're going to get to this in the next section. But I'm kind of curious. Certainly that happened in the past as well. And is that the same?
Thermohaline.
Yeah.
That is a little bit different. Thermohaline really just has to do with how heat generally and waters are mixed. And thermo is temperature and haline is the salt. And there are these huge, for example, deep water currents that sink off of Antarctica and then they run towards the equator and they cause mixing in these big currents. So it's kind of a different thing. What you're asking about is definitely true, and that's more related to that diagram that I showed and did not go through with all the equations, the chemical equations, and really is what's known as the solubility pump. And the solubility pump is part of the carbon cycle that I'm going to talk more about here in a bit. And it's the way that carbon dioxide in the atmosphere is absorbed into the ocean and released from the ocean. And there are a lot of factors that go into it that have to do with temperature and other chemical proportions. The key factor for, I think, your question is that it's a question partly of rate. And that, yes, carbon dioxide can be absorbed by the ocean, but it doesn't do it quickly. And that's why in these warmings and coolings that we looked at before, particularly with the coolings, they can recover after a warming, but it takes much more time than the spike in temperatures. That's related to how quickly it can absorb that extra carbon dioxide.
You had that slide where the volcanoes, they think of volcano clouds that rise. Do you have data showing the amount of carbon dioxide that volcanoes release compared to the amount of particulate carbon and other materials which the volcanoes release into the atmosphere?
I do not have a slide with that. Those are data that I could get, and I don't have them on the tip of my head. What I will say in terms of the volcanoes is this hinges on analyzing the other gases that were found with carbon dioxide to try to get at the source.
In an earlier presentation, you had greenhouse Earth versus icebox Earth. Could the transformation from greenhouse to icebox be due to the sequestration of carbon dioxide, for example, in large deposits of coal and also large deposits of oil? You know, kind of took it out of the environment, took it out of circulation, and because there's a link between temperature and CO2 that caused the temperature to drop?
We think it's primarily related to these tectonic changes, where basically because Antarctica was connected to South America and even earlier to Australia, it blocked ocean circulation. And as I said earlier, oceans are really what circulate most of the heat that's in the Earth. And when that opened up, it created more of a divide in where the heat was and allowed Antarctica to become thermally isolated. And by that I mean it allowed it kind of a snowball effect on Antarctica, which then created those glaciers. And that seemed to set off what was essentially an irreversible change in our climate into this ice house. And I think the only way, probably where we'd get a comparably large change, or at least, let's say, an analogous change, would be major changes in the configuration of the continents, at least in using that model. So I don't think, and I think most people think, it wasn't the carbon that was the main issue with that, although that certainly would have affected the solubility pump and everything else because it's changing these circulation patterns.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Darren Croft. Dr. Croft is a paleomammologist and is professor of anatomy at Case Western Reserve University's School of Medicine. In the second part of our talk, we learned about ice ages and interglacial periods, and how atmospheric carbon dioxide levels correlate with temperature. In our final segment, Dr. Croft will talk about the climate change that is being driven by the greenhouse gases humans pump into our atmosphere, and how that is affecting the weather. Now, back to our talk.
We'll finish up by talking a little bit about the modern era. And the carbon cycle. Thank you very much for those questions. And this is, I think, a nice diagram. There's a lot going on, and we're going to walk our way through it. The carbon cycle is how carbon cycles through the Earth. And there are producers of carbon, particularly carbon dioxide, among them plants. Plants emit carbon dioxide. We think of them taking in carbon dioxide, and that, of course, they do. They're very important, but they also respire it. We respire it, as do all other animals. That's a big cause of CO2, or something that contributes CO2 to the atmosphere. And these are the main natural sources of that, at least in the biosphere. In terms of sequestration of carbon dioxide, plants are really big on the other side of the equation, right? Photosynthesis takes photons with carbon and with water, and it makes them into food that can be consumed by us and other animals. And also decomposition of the plants themselves, as well as us, that puts carbon back into the soil. And this is really the main fast cycling of carbon. And as we said before, we also get a whole separate, well, not entirely separate, we get another carbon cycle that's in the ocean itself. Has a lot to do with chemistry and is also very, very important. The take-home message here is that we have certain producers of carbon dioxide, we have certain ways that it's sequestered, and these are more or less in balance. Fossil fuels are interesting because these really lock it up from this fast cycle. All of these things I'm talking about are relatively fast cycle. These are things that cycle through on the order of hundreds and thousands of years, whereas volcanoes, those are millennial scale cycling. That's a long cycle. Fossil fuels, they take carbon out and they lock it up where you can't get to it, unless you burn it. And if you burn fossil fuels, you are taking carbon and releasing it into this fast cycle. And that's really the issue that many people have with burning fossil fuels. This is, I think, a nice diagram for showing how this balance works. Lumping together vegetation and land, you can see that there's a little bit more sequestration of carbon dioxide than there is carbon dioxide being emitted to the atmosphere. And the same is true for the ocean. And if you add both of these up, basically we get 12 billion tons that are being sequestered into the Earth. When we add in fossil fuels, we're currently at 23 billion tons, and therefore this changes the arrow. And we're pumping more carbon into the atmosphere than is being sequestered. And that's really what's throwing off this balance. To put this in a different perspective, how are carbon dioxide levels compared to what we can measure in the past? This is a graph showing just CO2 for the past 400,000 years, although it's typical of what we've seen for the past 650,000 years. And you are here. And that is supposed to be off that orange because this graph you'll see is 4 years old. And that's how fast we're going up in atmospheric CO2. We're now up to 410. These are temperature proxies. And this is only through past couple thousand years. All sorts of different ways to measure temperature. I think you'll agree they're all over the place, but they show more or less the same up and down. The important point is that the past 30 years is the warmest 30-year interval in at least 800 years, and probably in the last 1,400 years. And this doesn't matter what proxy you're using. They all say the same thing. This is the graphic that I showed as you were coming in. If you didn't take a look at it, or even if you did, I'll explain what it is. This shows temperatures since 1880, and they're measured relative to a 30-year period in the 50s, 70s, 50s, 60s, and 70s, so 51 through 80. And as you'll note, when we get into the 70s and up into 80, it's a general even match between blues, which are a little bit colder than normal, and yellows, which are a little bit warmer than normal. But as we get to where we are now, all of a sudden it turns red. And that shows that virtually everywhere you are in the world, no matter where you are in the world, your temperature is on average 2 degrees warmer than it was back just a few decades ago. And we'll let that cycle through just a little bit longer. Here we are. Note, it's basically even blues and yellows. All of a sudden we're getting into the 80s, getting a little bit warmer, mostly yellows, 90s, 2000, and that's a lot of red. Now you might ask, isn't change normal? But isn't extinction normal? Extinction is normal, and change is normal, but. You'll see that we have lots of cycles. And change definitely is normal. particularly for the last couple million years. We have these swings between glacials and interglacials, and I like this cartoon, this idea of little Calvin on his swing. And he's not done yet because it takes him more than one recess to wear himself into a state of submission. And I think that's about what it is for the Earth. It really takes a lot to wear it into a state of submission. Thank goodness for us, right? We can go into these glacials and interglacials and come out okay. Change is normal. The question is if we're jumping off the swing. And if that's the case, then all of a sudden, we are really in uncharted territories. What do the paleoclimate data say about this? Are we still on this swing, or have we jumped off yet? What we do know is that there is no record of sharp CO2 change without temperature change. You can see it happen in the reverse, but you never have a big change in CO2 without a big change in temperature. We also know that carbon transfer between terrestrial and marine ecosystems is important for glacial-interglacial transitions, like we showed with the Younger Dryas, all these feedback loops. We also know that CO2 release is faster, much faster, than CO2 absorption. And it's not just an issue of magnitude, it's an issue of rate. The question now is, can the system compensate? This is a graph of CO2 versus temperature for the past 400,000 years. All the different points that we can take, and they're all within this little ellipse. That's where we are now. And that arrow is accurate based on that Y graph. That's how far off the graph we are. The oceans definitely can absorb CO2, to the question that we had earlier. They can. The challenge is it's not going to be enough, and it's not going to be fast enough for our lifetimes. If you're on a tectonic time scale, no problem. So we're really in uncharted waters right now. The questions that we would like to answer are we in a transition period to a new stable domain? Hopefully it's something stable. What are the main forcing factors and feedbacks of this transition? What will the climatological features be of a new domain? And what will be the responses and the feedbacks of Earth's ecosystems? Just to reinforce a little bit where we are right now, on April 19th of this year, Mauna Loa Observatory in Hawaii recorded its first ever CO2 reading greater than 410 parts per million. Now that number may not mean anything to you. So I'll tell you that records have been set every year since measurements began in 1958, when we were at 280 parts per million. That is incredible. At the current pace, CO2 levels could reach levels unseen in 50 million years since the early Eocene. Remember that Paleocene-Eocene transition? That's the same Eocene. That was in the hothouse, the greenhouse. Temps have risen about 1.8 degrees Fahrenheit since 1895, essentially since the Industrial Revolution, and sea level has risen about a foot. That's where we're at right now. So what happens if we just stop? The issue is rate. Earth is not in a hurry, and it works on a geological timescale. Humans are usually in a hurry. Earth works very slowly. Latest data, Proceedings in the National Academy of Sciences, says present changes are largely irreversible for 1,000 years. So if we stop what we've been doing for the past 120 years, we can maybe recover in 1,000 years. It's not a great ratio. We might be able to restore atmospheric carbon dioxide to pre-industrial levels on a much longer time scale. If you have 10,000 years, 15,000 years, 20,000 years, we might be able to bring it back down. Might. But we think it's going to be irreversible if atmospheric carbon dioxide concentrations increase to 450 to 600. And just again, to put that in perspective, we've gone from 280 to 410, and now we're saying we're in real trouble if we go from 410 to 450. What's that going to mean for mammals? For those of us who are mammal lovers, well, they can relocate. This is something that mammals do all the time. Humans do it all the time too, Florida. Like this moose. Moose tend to live in cooler habitats. Maybe they can just go up north. That's something that does happen. The challenge with relocation is that we're not in the same world we were 10,000 years ago. Humans make lots of roads, we have lots of development, and it's getting more and more difficult for animals to relocate. They can adapt. Now, they're not going to adapt like this deer on the other side of the fence. Fortunately, the other side of the fence in my backyard. Mostly behavioral adaptations. Mammals can adapt, but as I said earlier, usually this takes a long time. 10,000 years, 100,000 years. They don't have the time. This is a rate problem, and it's going to be really challenging for mammals to adapt. And then, of course, the other option is extinction. We're seeing some ecological effects already. We have shorter winters, warmer temperatures causing a boom in the tick population. 70% of moose calves across Maine and New Hampshire are killed by ticks. And this is sort of gross. This circle, those are all ticks that suck the blood out of these calves during the winter so they can't survive. The New Hampshire population is down from 7,500 to 4,000 in 10 years. And the likely result is relocation. Moose are going to retreat northwards where longer winters will keep tick populations down as long as they have a place to go. We see ecological effects in bird migrations that are changing. Now, these may or may not be bad. Some of these are just changes. And a lot of what scientists are doing here at the Natural History Museum and elsewhere are just trying to figure out what do these changes mean. For some things, it's definitely going to be bad news. But what does this mean for us? Extreme weather. And I put that asterisk there to emphasize, again, weather versus climate. Weather is often what we're concerned with because it involves what we're going to do tomorrow. Hurricanes in the southeast, more fires in the northwest, drought in the southwest. We think about global warming, we call it global climate change because it really varies depending on where you are. And sure, some places it's going to be hotter, which can cause death. But a lot of places it's also cold, which not only causes problems for people, but also our food sources. And in our neck of the woods, it's floods. Think of the huge rains that we get. We have droughts, and then we get inundated with 3 inches of rain. This is normal for extreme weather. Economic effects. If you don't care so much about the environment, how about your pocketbook? Or if you just like a good cup of coffee. Coffee leaf rust in Central America, where a lot of our coffee comes from. In 2012, farmers lost 50 to 85% of their crops, $500 million in damages, 350,000 laborers out of work. And the reason for this has to do with changing climate. The fungus has been reported in Colombia and mountainous regions previously too cold for it to survive. Where it used to be ideal to grow coffee, it's getting warmer and now we're getting new pathogens, new diseases. How about geopolitical effects? Melting ice is opening up new sea lanes, energy sources, and tactical ground for which Russia and the US will compete. On the other hand, you can now take a cruise to the Northwest Passage, and you can see a polar bear from the comfort of a luxurious cruise liner. Some of these things may not be so bad, but they may not be ideal for the polar bears. Other geopolitical effects. Warming oceans have forced fishes northward into disputed territorial waters of the South China Sea, raising regional tensions and forcing US military to step up its presence. We don't usually think of the South China Sea as having anything to do with climate change. How about the 128 US Navy bases that would be underwater if the oceans rise 3 feet? Cleanup and relocation costs estimated to be in the tens of billions of dollars. Mass migrations forced by flooding could lead to radicalization of marginalized peoples in regions already challenged by violent militant groups. Think how many people are living, particularly in tropical areas, down close to the ocean. Think what happens to their homes if the sea level rises a few feet. They got to go somewhere. Defense Secretary Jim Mattis said climate change represents a significant national security threat. One that, quote, is impacting stability in areas of the world where our troops are operating today. Something to think about. But I don't totally want to end it on a downer. There are opportunities. One of the things we need to do is cut down our reliance on fossil fuels, and Ohio is a great place for alternative energies. Things like windmills, creating solar panels, and hopefully this is something maybe some of you in the audience can take advantage of and really promote these alternative energy sources. By the way, there is always a rainbow over Case campus. And if you're gardeners like me, I can grow a lot of things I couldn't before, and I'm just waiting for the day where I don't have to cover up my fig plant in the winter, and I could just leave it out there and have a huge harvest of figs next year. So there are a lot of changes that may not be negative, but I think the one thing that is certain is that there are a lot of changes, and we have to start getting used to change.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.